Okay, so part 2, the halting problem. I should have looked up how to pronounce Entscheidungsproblem. So that's a German name. Hilbert was German. But halting problem. So this is usually taught in terms of Turing machines, but I'm going to teach it in terms of C, because until Monday you hadn't seen a Turing machine, maybe. But I hope you had heard of C, seen C programs. So, and if I teach it in terms of Turing machines, you think, yeah, this is something nobody would ever really think about, except these people who think about infinity. But actually, this is something, if you think about it in terms of C programs, this is something you might want. So when you program, if you compile, you're like gcc-o myprogram.c, sometimes it will come back and it will warn you about certain stuff. So it will warn you about, you're assigning something to the wrong type without a cast, and your various things that it will catch at compile time. So you don't have to run the program and have it sig fault or something like that before you find out that you've written a program that is bad. So what you might like to, before you actually, when you compile, you'd like to know, does this program, for example, does it fall into an infinite loop? So sometimes the compiler could, I mean, there are times when the compiler can figure that, I'm not sure if the compiler actually warns you about that, but it warns you about some stuff. So it would, in that case, you would like, before you actually, you run something, sometimes you run something on you have a file, you run your program, and it seems to just die. Right? I mean, it keeps going, but it's not doing anything. You think, oh, it's fallen into an infinite loop. Well, it would be nice to be able to get the compiler or something to analyze that, right? To tell you, does this program on this input go into an infinite loop? Now, actually, technically, since your computer has a finite memory, it has a finite number of states. So, well, it's connected to the internet. So, but if you cut it off from the internet, then it would have a finite memory. I mean, okay, everything's finite. Even the internet is finite. But harder to reason about. So if you say, okay, how many states? If I have like 32 gig of memory, so that's 32 billion bytes. So, and each byte is 8 bits. How many states can my computer be in? Well, each bit is 0, 1. Okay, let's forget that you've disconnected the hard drive. Let's pretend you've disconnected the hard drive as well. It's 2 times 8 to the 32 times 10 to the 9. Okay, so this is a big number. Okay, that's how many states it can be in, but it's finite. Okay, so let's see, but it's big. Okay, so now remember, when we talk about Turing machines, we're talking about something with an infinite tape. So it doesn't have a finite number of states. But just for the sake of this class, we're going to pretend that you're working on a computer, and if it needs more memory, it can get it. And we're going to ignore things like word size. Okay. Okay, so let's suppose, so Turing showed that you can't do this. Now, he showed it in terms of Turing machines, but and the proof that you can't do this is a diagonalization. So remember this is like mathy judo. So what is going to be a proof by contradiction? So we're going to assume that there exists this way, this algorithm that given a string, a program as a string, a C program as a string, and an input as a string, it's going to say whether that program ever halts on that input. Okay, so by the Church-Turing hypothesis, you could implement this as a Turing machine, and we're going to think of this as meaning that you could implement it as a C program. Okay, so I like C programs. So let's assume there exists a program a C function halts program string okay, so this is actually going to be, I will put in the type, whatever. So this is going to be a string. This is, so a pointer to character, prog string, char pointer, input string, that says whether a C program encoded in prog, well, C program prog string. So here we're going to think of it as a program, whereas here, but it is a string. It's a string where if you run it, it's a program. Halts on input string. Okay. So in particular, what we're going to assume is that if the answer is yes, then it will come back and say yes. And if the answer is no, then it will come back and say no after some finite time. So obviously, if the answer is yes, you can just run prog string on input string, and then when it does eventually stop, you can come back and say yes. So in the case of where the answer is yes, we can do this. So if you only wanted to sort of tell you for yes stuff, then you can do it. But so the problem is, can you do it for the no stuff? Because if you just say, okay, well, I'll be able to tell you this, I'm going to take prog string and run it on input string, but if it doesn't halt, then I'm never going to come back and tell you the answer because I'm going to be waiting forever for prog string to halt. Okay? So what we're going to care about is getting the no cases, okay? The cases in which we should say no. I wish I could turn this screen off because it's laggy and it's like looking at a weird reversed mirror that's a second behind, and it's freaky. But last time I tried to like blank the screen, it cut off the video, so I had to record the whole thing again. So so this is, we're going to assume there exists a C function, halts, that takes a program string and an input string, and does this. So that's the beginning of our diagonalization. So so in particular, we can write, well, okay, consider, then we can write a C function okay, I'm going to do this in red. Self-halts. So this only takes one argument. Okay, this only takes one argument, prog string. That says whether program prog string halts on input prog string. Okay, so this says we take the string prog string and we feed it to the program prog string, and it's either going to halt or not. And you think, why would you do that? Well, that's actually something we do. For example, when you build a compiler, okay, so one of the ways that people used to, back when I studied compilers, they were still doing this, I think. You would write your compiler, you would sort of compile it, and then to see if you, back before when you did the first compilations, one of the tests to see whether it was right was you would compile it with itself, right? So when they wrote the first, you write the compiler in something else, you compile it, and then you run it on its, you write it. I have to get this right. So I think the story is when they wrote the first C compiler, they sort of compiled it manually, and then they compiled it with itself and saw if they got the same result. And I think, oh man, it's been a long time since I did compilers, but I think one of the things is you still do this as a test. Maybe. Yeah, but usually you don't write compilers in themselves. Anyway, so got sidetracked there. Okay, but this is something that we actually do. So for example, if you're doing analysis of programs, you can feed the program to itself. So if you're doing like analysis of how much RAM does something use, you can actually okay, for example, something you should have seen. If you do PS, so you list the processes, it's going to list PS in there. Okay, so this is when I mean this idea of Matthew Judo and diagonalization, it's self-referential. Okay, so you talked about the order of the numbers of the reals in order to build a reel that wasn't in there. So we need to sort of talk about programs running on themselves to get this counterexample. So it's sort of like if you get into like I am lying, that kind of thing, that's, I mean, it's a children's game, but it's also that idea of self-reference it gets into some really weird mathematics. So Russell's paradox and things like that. Okay. So if this existed, if there was halts, then you could definitely write self-halts. I'm going to put halts in red too. Why? Because how would I write self-halts? Well, self-halts calls self halts, this is capital, self halts prog string. So simply, I'll take that bracket out because it gets confusing. Calls halts prog string, prog string. And then if halts prog string says prog string halts on prog string, then self halts prog string comes back and says, yes, it does. Okay, so it calls it and it says yes. Self halts calls halts and just says whatever halt says. Okay, so if this exists, then this exists. Okay, that was pretty easy. So now, what we're going to do is write a, okay, this next step is a little bit, so we're going to write a program called, let's call it opposite. Let's write this in red. So right, self halts is a C program, a C function. Okay, so actually, then so we can also write a C function opposite char pointer prog string. That calls, that halts if program prog string does not halt on input prog string. So if and halts on and halts otherwise. Okay, so what is this going to do? I've run out of board space. I've been writing too big. So how does opposite work? Well, opposite, I have a little bit of space down here. So opposite prog string calls self halts prog string and if let's just say self halts, prog string says yes, prog string says yes, then goes into an infinite loop. And just stops otherwise. Oh, you can actually see this. Okay. So actually now, so if halts, I should have used this space. Ha, fool. So we know what halts does. If we can write halts, then we can write self halts. If we can write self halts, we can write opposite. So let's actually see what opposite would look like. Let's write opposite, just so that this isn't some sort of abstract, weird idea. And let's write it where we have this definition of halts. So you have a video, so you can go back and forth. So void opposite char pointer prog string if self halts prog string then for else return right? That was easy. So if prog string halts on prog string, then this drops into an infinite loop. Otherwise, it just stops, it returns, okay? And in fact, if we wanted to say, well, we could also write self halts out like this. We could, I'm not gonna bother because this has already taken 23 minutes. But you could, it would be basically the same, like bool self halts, well, in self halts it can return 0 or 1, so I said a boolean if you've declared that, if you have that type. And then it just, instead of calling self halts, it takes prog string and calls halts on prog string like we set up here. Okay, so that's fine. This is normal so far, right? Sort of normal. Okay, so now tell me the behavior of opposite if I pass it. So opposite is a C program, a C function. And self halts, I can expand self halts is a C function. So it's a string. If I cat self halts.c, it's a string. I can see it. So, and I can expand this out. And as I just told you, it would be like basically the same kind of thing, but calling halts. And then halts is a C program. Okay, so it's a string, so I can expand it. So actually I can write this out, and instead of calling self halts, I can actually just expand that out, and I can expand it halts out, and I can write it. And I can write this whole thing as a string, right? If I have self halts in the same file, if I have the function self halts in the same file, and I have halts in the same file, the whole thing is a string. So I can look at this whole thing, opposite.c, as a string. And I can pass it to itself. And what does it do? Well, if it's going to call self halts on itself, on opposite, and self halts is going to call halts. And now, so if opposite halts on itself, then it drops into an infinite loop. And if it doesn't, then it halts. So I've got a contradiction. So you can't do that. You can't write halts. And actually, there turn out to be a lot of things you would like to do, you would like your compiler to be able to tell you, and frequently they just can't. So there's actually, I think it's called, oh man, it's been years since I looked at this. I think it's called Rice's theorem that says basically the big class, I should look it up. It's actually in the books just over there, but, or you could just Google Rice's theorem. The scribes can do that, or you can do that on the assignment. No, I think that would be mean. Yeah, I'm not going to put Rice's theorem on a third-year assignment. I think my master's supervisor did. I was the TA. I can't remember if that was a grad course or an undergrad. That was an undergrad course. Wow. Okay, so we're past 25 minutes. So the thing is, you can't write halts. You can't write a lot of stuff that's sort of like halts that you would want. And I remember one time I was at a workshop and somebody was saying that they'd done something and they were talking about people from Microsoft. And the people from Microsoft had said to them, we want that. We want it so bad that even if you prove it's impossible, we're going to keep trying. Now, actually, that's, in a lot of cases, you actually can tell if the program's going to halt. Right? I mean, obviously, you look at the program, and if there are certain things in there, then it's not going to halt. And if you can check certain things, then it will. And so if it's probably, but in general, you can't. And it's not like you can, but it just takes a long time. You just can't. Okay, so this is incomputable. Okay, so that's the Entscheidungsproblem. And the implications of that are big. So you don't actually get into that stuff if you watch Imitation Game, which is not super accurate. It's not accurate at all. But it's fun. So you can see Alan Turing played by Dr. Strange. Okay. This stuff, I mean, you see it, and I hope it's a bit easier to see it doing C programs than doing Turing machines. So don't worry if you see it and then you walk away and later you're thinking, how did that go? Diagonalizations are a bit counterintuitive. Okay, next stop, Kolmogorov complexity. Okay, stopping.